Welcome everybody. This is another of the tutorials of the Restart tutorials on telecommunications series. This is actually part 2 of the tutorial we had last week, and the title is From Automation to Orchestration, the New Frontiers of Network Softwarization. So we have the pleasure to have with us Domenico Scotece. Domenico is an assistant professor at University of Bologna. He has been working on this topic during his career, and he will present us, the part that continues the topic with respect to the one presented by Gianluca Davoli last week. However, the tutorial is self-contained, and Domenico will help us, to connect to the topic with a brief introduction.
Sure.
So enjoy. I will connect for closing the registration at the end. I just want to ask everybody to keep the questions until the end of the tutorial. So we will have 1 hour presentation plus the time that we want for the Q&A. For privacy reasons, so we cannot have the questions during the tutorial. Thanks a lot.
Thank you, Antonio. So again, good morning to everyone. This is the second part of tutorial that Gianluca presented last week. So this is, as Antonio said, it's self-contained. The first part was focused on the history of network softwarization from SDN to how orchestrate networks today. But this tutorial is basically focused on how to split an SDN controller and how to use an SDN controller in a microservice way. At the end, I have also a practical part. We are developed a new SDN controller from Rio SDN for sure that leverage microservice aspects. Okay. Okay. So as you know, as you saw last week, what is SDN? What is a software-defined networking? Basically, an SDN split the network into different plane. One that is a data plane, which is contain switches, hosts, and network devices in general, to the control plane. So the control plane actually controls how the data plane works. This is the principle of the SDN controller. But what is the problem today? The problem today is that the SDN as a software is a monolithic software. Okay. Of course, you can distribute SDN in a virtual machine, in a container, in the cloud, but you have the problem that if you want to have distributed SDN controllers in a topology, in a network, you have to replicate some that function of the SDN that could be unnecessary in a certain locality. Okay. So what is the basic idea is to split an SDN controller in a microservice way. Okay. So in the way that you can have different functionalities of the SDN in a form of microservice, in the sense that you may have only a specific function in a locality, another specific function in another locality, and so on. So a brief introduction of SDN elements, in particular network elements. An SDN controller the control plane has to manage devices, links, hosts, and packet flows. This is the elements that an SDN that a control plane has to manage. And also, there are some common function. This is the elements that the control plane has to manage. This is the function that controls actually the elements. That could be routing, that is a basic functionality of the SDN. Topology, that manage the topology of the network, but other different functionalities, let's say policy, performance monitoring, discovery of link or devices, network state, and so on. But also, actually, I didn't show you before, there is another plane, okay, that is called the application plane, that is on top of the control plane, that contains external application. External application means firewalls or other applications that can leverage control and data plane. For instance, this is a set of common application, virtualization, slicing, firewall for sure, security, load balancing, performance monitoring. Okay, those applications are applications that leverage control and data plane to perform some functionalities. Okay, what is the limit of an SDN controller today? As I told you at the first slide, the problem is that the software is monolithic, and for instance, if you want to have a distributed controller, it's possible today to have a distributed SDN controller, but the problem is that you have to replicate the whole software in order to manage the SDN controller. This is true, but the problem is that you could have some unnecessary functionalities in a locality. Imagine that you are running with resource-constrained devices, Raspberry Pi or other kind of low-constrained devices. You want to maximize. Also, you want to minimize the cost of the distribution of SDN controllers. So this is why the idea to have a microservice-based SDN controller. And also, another problem is that the modules are tightly coupled, so we can leverage microservice to have decoupled functionalities. And also, in a distributed SDN controller, the problem, if you have a phase of a single controller, you have to use a central controller. In other hand, also a distributed set controller uses a hierarchical SDN topology. So there is a macro controller and then the distributed ones. So the basic idea is to decompose the monolithic SDN controller into different sub-functionalities. And then you are able to deploy functionalities that you want in a locality, and then you can have the deployment in form of virtual machine, in form of Docker container, so you can dynamically scaling, and also you can start up or shut down on demand which functionalities you want. You can play with, you can leverage orchestrators like Kubernetes if you want to run it in Docker container, open source Mano, for instance, if you want to leverage a virtual network function. And then also We have a lot of benefits like reducing the code size, dynamic increase the number of functions and resources, and so on. This is a very rapid tables in comparison between monolithic SDN controller and decomposed SDN controller, but is a design principle which sorry, it's for all design principle. For instance, scalability, cloud, loss coupling is the difference between having microservice or not. This table. For instance, for scalability, monolithic SDN controller means that if you want to scale a system that leverage a standard SDN system, you have to replicate the whole SDN, okay? In terms of software components, if you have an instance of the SDN controller in a locality you want to scale, you have to replicate the entire piece of software, okay? In a microservice way, in a decomposed SDN system, you just have to scale the function that you want, okay? That is the advantage is to have microservices instead of monolithic. For cloud, of course, you can virtualize, you can containerize a whole microservice, SDN system, but it's very bulky, okay? For instance, ONOS is almost 1 or 2 gigabytes of code, so you have to containerize or virtualize the whole system. For a microservice, for a decomposed SDN system, you can have a different piece of SDN functionality that you can put in a virtual machine or in a container. It's just a small piece of software. Loss coupling, for sure, in the internal modules are typically in a monolithic system is completely decoupled. So this is the design of a monolithic software. In a decomposed way, you can have a more flexible environment. If you imagine that you have different locality and different microservices that act SDN function, you have decomposed the whole system is an SDN, but you have decoupled the single functionalities. Other principle is maintenance. For sure, if a monolithic system fail, you have to locate one. You have to run another SDN system, so may take a very, very long time. For a decomposed microservice SDN system, you can for sure isolate the problem, isolate the fail, and then you can only replicate the function that fails by leveraging an orchestrator, let's say Kubernetes, for instance, or just Docker or just Docker app, or Docker run. Just you can run the piece of software that you need to replicate. And also is the same for component reuse. For a monolithic system, it's very difficult to reuse another subcomponent. The problem is that this tightly coupled the internal component in a monolithic system, and then you cannot isolate and replicate some component in a microservice SDN system. For sure, it's true the same that we said for maintenance. You can reuse part of component. Okay, this is our architecture, the architecture that we have in mind for the composite SDN controller, let's say microservice-based SDN controller. As you can see now, we don't have let's say, the difference between application plane and control plane. Okay, the idea is to have multiple microservices that can act as control application, let's say routing and topology manager. Okay, that we saw before that routing could be a default application for SDN control and also topology, but also at the same plane we have external application. Okay, because each acts as microservices. So here the idea is to manage application and the control plane in a single plane, let's say control application plane, and all applications are microservices. Okay, in this slide we show the architecture with this is a Mano standard. Okay, because the idea is to use a standard solution just to show how this could be orchestrated in a standard architecture. Let's say there is an orchestration of microservice application, and that's internal application, external application, and also there is a virtualization layer and infrastructure layer. That is the Mano standard. Okay. This is what I said before. External applications are incorporated inside the application, and then there is no more northbound interface. Okay, we just collapse the application plane and the control plane. We merge the control plane. This is a possible. This is a slide. It's just a possible deployment. Okay, in this slide. Also, there is a possible deployment using, for instance, Kubernetes. The idea is to have a network layer with network protocols. Okay, I can show you later which kind of network protocol we use it for this project. Actually, we use the REST because REST is a standard also for 5G control plane, gRPC and WebSocket. But the important part is that there is a network adapter that you can leverage for connecting those applications at the network. And also there is a network state, let's say state that should be synchronized for sure. And also a protocol that is a discovery, that is a discovery protocol for discovering the application. This is the application layer that the application protocol layer that we used. RESTful API because it's standard in 3GPP service-based architecture. So 3GPP released 15. Okay, but also we tested other different network protocol, let's say gRPC, okay, that is a Google RPC, is an open source network protocol, and also WebSocket. These protocols are used to make the communication between SDN controller sub-functionalities and also external application. Okay, this is the protocol that we used in this kind of architecture. Okay, this is actually the implementation that we used. We leverage Rio. I don't know if you are familiar with Rio. Rio is a SDN controller written in Python. Okay, it's very simple. Okay. What we did in this project is the main idea is to isolate the core part of the SDN of the controller, because RIU works with OpenFlow and is event-driven SDN controller. The idea is to intersect an event, okay, because it's an OpenFlow. As you can see, the control plane is the blue line. The event is intercepted by a module, a specific module, and then the basic idea is to transform an event to a REST API. Right? In this way, we can have external application and also SDN application. Let's say simple switch is a routing application. It's an application inside the SDN controller as a external application with the REST. For instance, this is a network protocols, but for instance, REST, okay, with a REST interface. And then we can transform an event, an OpenFlow event, in a REST API. Okay? In that way, we can just only have the middleware, that is the core of the controller, in a containers, okay? And then different containers that contains application, SDN control application or external application that expose a RIU, REST interface. Okay, this is the way on how we transform RIU, the standard RIU, in a microservice way RIU controller. Okay, this is our publication, and also I will show you the project, the link to the project. Okay. Okay, this is what I said before. We isolate the emitter, that is the event emitter, is the core of RIU framework, the SDN controller, and then we create the support module to create the REST communication. Okay, so the middleware is actually the core of SDN controller, just the micro part of the core of the controller, and then we turned each RIU application in a, let's say, SDN functionality in a separate microservices, okay? And then we connect this function to the controller via RESTful or gRPC or other network protocol. In our test, we want to show result in terms of latency, network latency for sure, and also in terms of reliability and scalability, and also we leverage a solution like bare metal for sure, and then virtualization in a virtual machine and containerization in a Docker container. And then we tested this solution that is called microservice SDN MSN. We tested the MSN in a Docker container environment and in open source manner with virtual machine, with the DNF, and in OpenStack as a cloud infrastructure. The test was done in a simple Ubuntu server machine with these characteristics. We used the open source manual release 8 and Docker community release 19, Python version number 3, RIU SDN framework, and also we used the microstack as the OpenStack infrastructure. And at the end, Mininet was used to create topology and to test the network. First, we evaluating the latency. We evaluating the network protocols with this kind of topology that contains a single controller, 5 switches, and then each switches contains 2 hosts. In total, we have 10 hosts. And also the latency test leverage the ping ECMP protocol, and we tested the 3 kind of messages. The first message is the message that creates the rule, okay? That takes more time than the normal flow. And then actually there is no in this figure, but there is the normal flow. The normal flow is the flow that with no latency. I'll show you later. But here there is the update messages because you can set the expire time of a single rule. For the first message, for instance, H1 wants to communicate with H3, okay? The controller has to create the flow rule, okay? The flow rule contains the path that the packet has to follow to reach the destination from the source that is H1, for instance. Okay, this rule still valid for the time that you can set. There is an expiration time. In this experiment, the expiration time is 5 seconds. After 5 seconds, this rule disappears, and then we have to update that rule. That's why there is the time that H1 update H3 is the packet that renew the rule that we saved before. As you can see here in blue there is a WebSocket, in orange JRPC, and in yellow is a REST protocol. For sure, REST protocol adds more latency compared to JRPC and WebSocket because it's a protocol that acts at the application layer, so it takes more time, but it is a standard. So that's why we continue to investigate and to develop in this REST, because as I said before, in 5G core network, REST is still using as the standard protocol. As you can see here, the distance between nodes, I mean, if we increase the distance, we increase, of course, the latency. H1 want to communicate with H10. There is an increase in the latency also for the update, not only for the first messages. Okay, this is a benchmark of the network protocol. This other test is the benchmark of different different softwarization. The first case is the bare metal, is a standard MSN. Okay, we have the same topology. We have the same architecture, the middleware application add let's say different layer, but it's the same application for SDN functionalities or external application. Okay. Also, we have the same development in a Docker container. Okay. And also we have the same development in a virtual machine. Okay. We tested these 3 different deployment solutions. Let's say softwarization solution. It's the same. Here we only use the REST as a network protocols, but we have different softwarization. In the first case, as you can see, Docker adds a bit latency compared to the standard MSN, but also you know that virtual machine use a different kernel as the standard one, so the latency is in, let's say, 2 times the standard one. But this is true for the first packet. This is not true. The situation is the same for the normal flow. Normal flow means that the communication between H1, H3, for instance, or H1, H10, when actually the rules is alive. So the flow doesn't go through the controller. It's just is a network delay between H1, H3, or H1, H10. So this is called the normal flow. The normal flow is the same because the packet has not to pass to the controller, so is the network delay. The situation is more or less the same as the first packet for the update. It's the same update after 5 seconds. Docker adds a bit latency compared to the MSN, but the virtual machine is more or less is the same 2 times the MSN, the standard MSN. Okay. Second part of this test is about resilience and scalability. For the resilience and for the scalability, we leverage open source Mano, and we leverage for resilience the auto-scaling functionalities. And then for scalability, I can show you later. We use two different scenarios to scale services. For the first test, we simulate a phase for routing functionalities. Okay. Actually, the idea was to leverage open source Mano auto-scaling, but to make that this is possible, before we preventively run 2 SDN routing, okay, SDN routing 1, SDN routing 2, okay. In this graph, you can see that there is a data plane delay and control plane delay. For the first time, you have a control plane delay. That means that you have to create the rule, okay. Here, after 20 seconds, we have the expiration of that rule, so that's why we have a delay in a control plane and also a bit in a data plane. Before what we simulate here, before the expiration of the second time of the rule, we simulate a crash in the routing functionality, routing 1 functionality, and then we changed in the controller, we changed the reference from routing 1 to routing 2, and then what we said is that we have only a bit delay on the data plane. Okay, the control plane works in the same. It works before, but the data plane, we have a delay in the data plane because we failed the first time to reach routing 1, and then we changed to the routing 2. That's why we have a delay on data plane, means that the packet have a delay to reach the destination. And then the same happens after 60 seconds. No fail, but we have to renew the flow. This is how we tested the resilience. Instead, for the scalability, here we leverage a microstack. So we leverage OpenStack as a cloud infrastructure, and the open source Mano as a standard for distributing the services as a virtual network function. But we have to distinguish between two definitions. Services and the network, virtual network function that is a single network function, and network services. Network services could be a composition of virtual network function. Okay, for instance, network services one in this example is the deployment of the whole microservice SDN system in our example, because it's composed of the controller, the middleware, and also the routing functionalities. The network service 2 is a copy, is a new deployment of the same network services composed of a middleware and simple reach. So here, scalability means that you have the entire replication of the SDN, also microservice based, but the entire SDN system. Also, we leverage a balancer in between the network and the controller that can move request also. It's the same for data flow request or control plane request from one system, one network services or to another network service. This is not the efficient way to scale the system that I saw before. We want to leverage the microservice. We want to leverage the micro functionality. We want to only to scale the macro functionalities. So this is a different scenario that we tested that is more close to what we want to test. Is that imagine that you have a mega network services, okay, that is composed of course, our controller, our middleware, and then multiple instances of real application. Let's say you can have routing application, topology application, and external application, okay? For instance, in this specific example is a routing application, and then we have multiple instances of routing application. So here the idea is to test the scalability of this scenario, and then to have a balancer in the controller. So the controller can send a request to let's say routing 1, routing 2, routing 3 to different deployment of the network function. Okay, this is the way, the second way to scale the microservice SDN controller. This is some results that we gather. We have scenario one is the first one. Of course, the first one in terms of latency performs better than the second, because the load balancing is at network level, is not at the controller, and our network service is self-contained because it contains controllers and functionalities in the same network services. And in the other way, in the second scenario, you have to balance the request after the controller, and then you have to choose which services, which application you want to reach, and it's a bit it has a bit latency compared to the first one. What are doing today, we are working on an extension of this kind of architecture. The idea is to leverage the intelligence, for sure. We want to look at the 6G, not only 5G. And the idea is to transform the microservice, the SDN controller microservices functionality as an agent. Okay, an agent is a same concept, so it's a software component, it's the same concept of microservice, but with the idea to have intelligence inside. Okay, an agent can create a functionalities from the intelligence that you want you put inside. Okay, the idea is to have a blank agent with a model that you want to train. Okay, and then this agent can act as a specific function thanks to the intelligence that you have inside. So this is the concept is you have autonomous elements that may execute a task. Okay, and also we have a different enormous capabilities that we can reach with the agent. I can show you later an example that we use the agent for shortcut path. Okay, to decide the optimal routing. Imagine if you have not simple topology, but it's a complex topology that you want to determine the shortest path because you have to maintain certain quality of service policies, and then the topology change dynamically and the behavior of the network change dynamically, and then you want to adapt the SDN controller to this change. You can for sure leverage an agent, and then you train it before an agent, and then you can use it to determine the shortest path, to avoid the congestion, and so on. Okay. This is what we did at this stage with MSN with the agent. There is a specific branch in our repo that is specifically for agents. Okay, we have two different, let's say, intelligent part. One is for the topology learning. This agent actually is able to understand what happened in the network, and then by using a specific library for network graph, network X, can recreate the topology. Okay, and then you can use it. You can use this knowledge to, for instance, determine the shortest path, to avoid certain path, maybe because there is an attack, there is an intrusion, and then you can for sure leverage this information to avoid this specific path. You can build whatever you want in this kind of architecture. Okay, this is the same architecture. This is the master architecture, but with the add of topology learning. As you can see here, topology learning is a new external application. Okay, it's a new Docker container, it's a new microservices, it's a new agent. Okay, in the network. Also, simple switch REST is the same that I showed you before. Is a routing microservice, but you can add intelligence inside. You can separate this intelligence. You can have a different containers, different microservices, different agent, one just that controls the routing facilities, and then the intelligent for building let's say intelligent path, for building shortcut path, okay? And also you may have another application, another containers, another microservice, another agent that controls the topology, controls what happens at the topology. This is the connection, this RX connection between these two agents. We create a new handler, is update graph, okay, and then we create a new is not here in this picture, but we create a new event. Actually exists an event in SDN in OpenFlow that is a switch enter, for instance. We translate switch enter event, the OpenFlow event, in a REST call for the topology learning, because we want to understand what happened in the network. We want to understand if the topology changed. So switch enter event is the event that controls what happened in terms of topology. And then when topology learning creates the new updates, the knowledge updates the graph that contains the topology, we can update this knowledge also at the simple switch, because if you want to do shortest path, you have to know other different intelligent paths. You have to know the topology and what happened in the network. Okay, this is the new handler that we had to connect these microservices. Okay. So in conclusion, what we proposed is a microservice-based solution for SDN. We want to intend this as a playground framework. It's not, of course, ready for production. Okay, it's just a playground solution that we want to use also in the restart. Actually, is the project in Super is a Super Orchestrator. We want to start to investigate the use of this kind of solution in the Super Orchestrator to orchestrate the services at the network, to SDN services. So this is a playground framework to play with the application or services that you want to add to the SDN. So this is a good starting point. Okay. And also we tested this solution with different network protocols, also with different softwarization, let's say virtual machine or containers, and we tested also resilience and scalability. For the future, so we are looking for solution for intelligent 6G networks. And also, as I said, for a starting point for Super Orchestrator in the Restart project. Okay, we have just 10 minutes. Just want to show you this practical example how this SDN works. This is just the links to the public repo. Okay, there is a standard branch that is the master that contains the first solution that I show you, and then there's the second one that contains agents and intelligence inside. This is the deployment that I want to show you. Is the same deployment with the 5 switches and then 10 hosts. Okay, and then we have 2 containers. One is the middleware that contains the control, and the other one is the routing is the routing application, is another containers, okay? What I want to show you is a simple ping, for instance, H1 ping H4, and then show you what happened. We can separate the data flow and that is the data plane, and with the control plane, what happened at the first ping packet is MP protocol packet. What happens is that is an open flow event, that is this packetin, this is the name of OFPP packetin, is the real name of this event, that is an open flow event, means that there is a new packet, okay, that there is no rule to forward this packet. So the first time switch one cannot send packet to everyone because he doesn't know the destination, okay? Just check to the controller, okay? The controller creates, the open flow creates the event, and then the controller transform, our controller, our middleware transform this event in a REST communication. So the packeting, the REST packeting is sent to the simple switch, and then there is there is a business logic here inside that creates the rule, okay? The function is add flow rule, okay? Add flow rule actually create the rule that contains the path. The path here is switch one, switch two, switch one and switch two, simple because H1 want to communicate with H4. For instance, H1 want to communicate with H10, the packet flow, the other rule contains the whole path is S1, S2, S3, and then S4, okay? This is very simple. The rule contains only S2 and S1, and then the packet is forwarded to the host, or the host 4, and then come back to the H1. And then next time that H1 wants to communicate with H4, the rule exists and is still live, because remember after timeout the rule expired, but in the meantime that the rule is true, the communication between H1 and H4 goes to the switches without go to the controller. Okay, it's a normal network communication. Okay, maybe okay. Just want to show you one example. Let me open. Let me open the desktop. Desktop one. Okay, maybe it's better to share the whole screen. Okay, so this is our repo. Is a public repo. Is in GitLab. Okay, this is the master branch. The master branch contains the first, not the agent one, but the first solution that I show you. It is composed of 3 different folders, let's say. Okay, the first one is a Rio apps. We call it the Rio apps, but it is a middleware. The middleware contains the emitter, that is the functionalities that intercept an open flow event, and then if there is an handler in this file, transform the event in a REST communication. Okay, this is the core part of the controller, and also we have another folder that contains all of network functionality that we want to add in this controller. This is the routing application, okay? That contains a simple handler. This one is a REST handler. Is a Flask. Basically it's a Flask Python REST API server. Okay, this is the handler packeting. Okay, and then when the core of the controller send a request here, there is a bit flow function There's a business logic that creates the rules. Okay, it's the standard one, but we just decoupled this function as a different components. As you can see here, the timeout of the rule is 5 seconds, and then this rule is installed all in the switches that has to install, and then the communication goes to the normal flow, follow the normal flow. Also, there is a README that you can follow to run. That I show you a simple example. I want to show you the Docker example. We have a pre-built image. We have pre-built those images. Sorry, the first one is the controller, the core of the controller, and then the simple switch. Let me run first the simple switch rest. Okay. This is a server rest that runs in a specific port. Okay. Let me open another window with another. I have to run run. Okay, this is the manager. Okay, that contains two different applications that I told you. The event handler that intercept event, and then the rest communication. So the rest module that transform that sends the event in a form of REST API. Sorry. Okay. We need to create a network. Okay. For creating a network, we have a minute script that creates the network. It's the same architecture that I show you in the slides. Okay. Scripts. Okay. So okay. Okay, what happened here? The system creates 10 hosts and 5 switches. Okay, they start to exchange some configuration messages. It's not part of it's part of the protocol, but not part of this example. So here the idea is to show you the messages that, for instance, the routing has to manage. For instance, if I want to communicate with H1, H4, let's say H1 ping H4. So as you can see here, after this is the first messages. After 5 seconds, we have an update. Okay. This is an update after 5 seconds. This is a different. After 5 seconds, another update, and then this is messages. This is the first 4 messages, 2 per way. Okay, switches 4, switches 1, switches 4, switches 1 for two times, switches 1, switches 4, and then after 5 seconds, as you can see here, after 5 seconds, we have to renew the rule, and then after 5 seconds we have to renew the rule, and so on. So this is the controller that contains a lot of messages that is difficult to navigate it. But no, this is a very simple example, a very simple idea to have a playground, let's say, to have a system. Again, is not ready for production. Is just a playground framework to play with a new, let's say, application for SDN controller. So if you want to test your specific application for security in a SDN way, you can just add your functionality as a microservices, and then you can add the handler, the REST handler that you want to intercept, and then you can test the functionalities with this solution. Let's just the time is ending. Okay, just to show you that this is the other solution is the agents one. As you can see here, we have also the controller that is the same, but also we have routing, that is the same simple switch, but also we have topology. And then into topology learning, we just add this kind of topology update and also host update, okay, to REST handler that actually the handler that coming from the OpenFlow is this one. You just check it, but just you have to add the handler that you want to manage, and then you can play with your code. Just fast check. This is how actually the controllers works. This is the event that is OpenFlow event. This is a standard event, say, for instance, OpenFlow packeting event, and then you have to transform this event in a REST API. So just in a post, okay. That way we transformed an event in a REST, okay. It's a post to a specific handler. This is hard-coded, but this is if you have a system, you have a DNS, if you have a discovery system, you can have a more complex system. But also this is the new event that we added in this specific branch is event switch enter. Is a switch enter that changed for sure the topology, and then we the same. We follow the same path, and then we send the, let's say, I don't see the post, but there is a, okay. This should be the post to the functionalities, okay. Okay, and maybe it's an update topology. Update topology, exactly. Send the post to the REST API. Okay, I'm done.
Thank you,
I
Domenico.
hope that is in time. Sorry for
yes, perfectly in time.
fast.
1 hour as planned.
Okay.
Thanks a lot. It was very interesting.
Thank
and
you.
Also, it was also a nice dive into your work in Restart, which is also one of the goals that we have in this series of tutorials.